think this is working. Okay, we're live. Alrighty. Internet was not working yesterday, so I'll try to review a bit of that. But if you, I guess for I don't know, talk to a classmate, maybe see the ones you missed. But a quick overview is just work is force times displacement. Later on, we'll clarify this a bit. It's actually, if you're thinking of this as a vector, it's actually the component of the force that's actually in the direction of the movement, but we'll clarify that later. For now, assuming that the force is in the same direction as the movement, this is valid. And then how much energy does the system gain? Well, the amount of energy gained is equal to the work done on the system. And then the last thing we talked about was how if you quantify that, your kinetic energy is 1/2 v squared. So anyway, let's go over one or two more examples, then I'm going to talk briefly about potential energy. So let's look at, these are all pretty fast questions. Like number 3 says a 100 kilogram block is initially at rest. Here's the floor, here's a 100 kilogram block. Let's say we expend 500 joules. Well, sorry, let me clarify this diagram. 100 kilogram block. We're going to basically be asking what is the final velocity of this if, say, the input of energy was 500 joules. Hello, Mr.
Knowledge. Caleb Smith here.
Yes, he is. No, we can't keep him. Okay, so anyway, you can solve this question. That's all the information you're given. Now, what you're going to notice is we're going to be able to solve this question without figuring out how much force is required or how much distance it moved or how long it took or any of that stuff. So we're going to go direct to relating if this much energy was inputted, was exerted, okay, or expended, then how fast would it be going? So that's what this is. Does that make sense to everyone? Okay, so assuming you expended this much energy to get it moving, you can assume, well, that's what conservation of energy is. You can assume that all that energy was converted into the block's kinetic energy. Now, in real life, nothing is perfectly efficient, but if any of you guys go on and further your, we'll talk about it. We'll talk about a couple scenarios where energy is not conserved. But anyway, if you take thermodynamics, that's the class where you really are focused on like how efficient is this system and stuff. But anyway, so the math is very simple. You'd say, okay, the kinetic energy of the block would be 500. 1/2. The mass is 100. Okay. So 500 divided by, that's 50. So that's 10. And so your velocity is going to be this, whatever the square root of 10 is, so 3.2-ish or something.
Start walking when you started, that's square root of 10.
And no, I did decimal. Okay. In mathematics, we'd write, if you're just solving this as a pure equation, you could write the exact number, but not that it would be wrong, but usually we round. Okay. Was that 3.16? Okay, so the moral of the story here is that we basically just did kinematics if you think about it. We effectively said, well, if I know how much effort or energy was put into this system, I can figure out the final state of the system without having to look at things like how much force was the winch exerting on the block, or how long did this process take, or things like that. All right. By the way, I'll give you some context here. I mean, does anyone here know another unit of like energy other than the joule? The calorie, very good. The calorie is one. How many calories are in a joule? Let's look that up. Calories are weird because there's kilocalories and there's calories, right? If you eat 100 calories of, like, what's an Oreo cookie? Like 100 calories, maybe 50, whatever it is. One Oreo? I don't know. Let's look it up. How? Taking bets. I bet it's like 40 in one Oreo.
I'm guessing I'm getting about 30.
That's what I was hoping it's about 30.
Well, you know those little tiny bags that are 100 calories?
Yeah.
You can just literally like eat that in one bite. And you're like, that was like basically one Oreo. Maybe it's 100. Let's see. One Oreo has, well, this is just, according to this person, 53 calories. So anyway, but you guys know there's like kilocalories and calories. A calorie is really tiny. So they go, when you talk about food calories, they're usually talking about kilocalories, but they call kilocalories calories with like a capital C, right? Anyway, that's more chemistry stuff, but anyone else know another unit of energy? That's,
We got taught.
we talked about one yesterday a little bit. Foot pounds would be a unit of energy. You know, we were talking yesterday about, oh, Mr. Crandall, hello.
Wait, what about watts?
Very good. But a watt is actually a unit of, it's a rate. It's energy per time. We're going to talk about watts in our next problem set. But if you guys probably haven't paid an electric bill, most likely, but if you did, you'll notice that they charge you by kilowatt hour, which is weird. You go kilowatt hour. So kilowatts would be how many thousands of joules per second. So like your microwave is probably 1 kilowatt, meaning it expends 1,000 joules of energy each second. If it was a 2,000 watt microwave, it would expend 2,000 joules per second. Anyway, if you multiply that by an hour, that's a unit of energy that they bill you at, and they bill you at like it's like a couple pennies per kilowatt hour. But anyway, it's kind of amazing to think about how much energy that is. If you run your oven for 3 hours to cook something, take the wattage of your oven. I don't know, your oven might be, who knows, it could be 5,000 watts. 5,000 watts multiplied by 3,600 seconds tells you how many joules of energy the thing uses. So it's a lot of joules. Okay. Anyway, so a joule is not a very large amount of energy. But, so yeah. The last thing I wanted to clarify yesterday was, so yesterday we talked a little bit about, like, say you have like a cannon or a gun. There's like a barrel, right? You can relate the definition, okay? So when, this is an oversimplification a little bit, but let's say this is a cannonball. Well, what happens when the like gunpowder is ignited, heats up, expands rapidly. When something heats up, it tends to expand. And what does that expanding gas do? It exerts a force on the ball, and then the barrel is long, so that force is exerted over some distance, and so the gas does work, right? So the gas exerts a force on the projectile, the bullet, the cannonball, whatever, over a distance. And so that's why you'll find typically the longer the barrel, the higher velocity the thing is, because you get a larger distance to exert the force over. Now, the thing I'm oversimplifying is this force actually shrinks. Initially, the force is a little bit larger because that gas is really packed into that small space. So technically, it's actually, if you have to do some calculus, you integrate the force function. But anyway, what's up? You have a question?
I was gonna say, like, keep on that topic, like, when you're like rifling, like a barrel, like, does that equate to like the distance of travel as well? Or is it solely just related to the force?
That's more just to get it rotating. So, so we'll talk later about angular momentum. You spin a top. If you spin a top, it can like stay stable. So anything that spins is going to tend to have some stability along that axis. So that's at least my understanding is that's the point of rifling a barrel is that gives that projectile stability. In the olden days, right, didn't they just have like a little ball of lead like back in the revolutionary times? And those were not very accurate.
Yeah.
So you guys, I mean, maybe I shouldn't bring up baseball, but anyway, if you've ever looked at baseball, you guys know what a knuckleball is? It's also a thing in soccer too. But
Yeah.
if you throw a baseball with no spin, it'll wobble because it's traveling through a fluid, it's traveling through air, and that tends to create like perturbations like in the airflow, these weird kind of like little pockets, and like it'll bop the ball back and forth. Where if it's spinning, at least a spinning sphere will take a nice predictable curved path. But like for a bullet, that's more cylindrical shape, so it'll tend to travel in a more like, well, they're traveling parabolically. But anyway, does that make sense? If the bullet were a sphere, it could diverge like a knuckleball, basically. Okay. Anyway, in soccer, back in like 2000, what year was this? I want to say 15 or 14 years ago in the World Cup, they introduced it's 18 years ago. They introduced a new ball, a soccer ball, that was very smooth. It had no seams. It was like a perfect sphere almost. And so what would happen is if you hit the ball really hard in the dead center of it, it would just like go pew, and just take these ridiculous like weird diversions in its path. And so it made it very entertaining to watch the World Cup because these professional players could hit the ball so hard and it would just go towards the goal and then just shoot off in a random direction halfway through its path. And so it was kind of like, I don't know, it got crazy because they kept scoring these ridiculous goals. But it was a fun ball. The balls were really expensive. They were like $200. But if one of your friends had one, you could take it out, and you didn't have to be like a professional. If you just hit it really hard, it would just be anyway. I've never been able to throw a knuckleball with a baseball. The same principle. Can anyone here throw a knuckleball?
You can hit a knuckleball, Mr. Hall.
Could I hit a knuckleball?
Yeah, no, with your foot like in soccer you can.
That's what I'm saying. A soccer ball's easier. It's a big, fatter ball.
Oh, yeah.
To throw a knuckleball in baseball, I think you need a lot of arm strength. It takes a lot, and the technique is very difficult. Because to release the ball with no spin is very tough. With a soccer ball, you just bop it. You just hit it really hard. Okay. Anyway, where were we here? Oh, last remark. That's why golf balls have those dimples. Right? If you ever wondered why does a golf ball have all those dimples? It's because if the golf ball didn't have dimples, you'd hit your drive and it would just veer off. It would be very frustrating.
Anyway. That's why golfing works anyway.
Well, if you hit a slice, you'll notice your slice takes a nice, predictable, like.
Predictable is a fine word.
I'm saying when I hit a golf ball, most of the time it does this.
Yes.
Of course, if I overcompensate, I can hit it like you can hit a hook or a slice. If you get lucky, you hit a nice little draw. Or is that a fade? I can't remember. Whatever. But I'm saying if the ball was smooth, what would happen is the ball would be trapped. So what happens with those dimples is the dimples make the airflow over the ball nice and smooth and predictable, which is kind of counterintuitive because by causing little turbulence, it actually overall makes it more smooth and like nicely behaved.
It causes vortexes.
Yeah, a little. But what's weird though, by the way, if you can fully solve this, I think it's called the Navier-Stokes. It's related to that. $1 million, you can become famous. Anyway, if the ball was nice and smooth, you'd hit your drive. You hit a nice drive, and it could just be like that. It would just hit like a knuckle, or it might go like it could take a weird path because of the air.
Well, that's like the golf ball thing. A lot of it's new within the last couple of years, but airplanes are getting these things. Well, I mean, they're literally just vortex generators, and they put them on the wing, on the leading edge, and so then it creates like a golf ball as dimples do, because then it increases like aerodynamics and all that stuff.
Oh, sweet! I didn't know that. It's interesting. Anyway, yeah, anything involving airflow or aerodynamics is extremely complicated. You can do it. You could do an entire career of research on just like, how a ball goes through the air. Anyway, so let's so all these questions are basically just using those. It's using k equals 1 half mv squared. So hopefully you can figure those out, not having too much trouble with them. So before we move on, what do you want to cover? Oh, okay. I think we'll have some work time tomorrow. I want to cover potential energy. So the rest of these are all just, again, it's just the same exact formula. It's just you got to think, how do I use that idea of 1 half mv squared to like analyze these problems? And then what you're going to find on these, I think tomorrow we'll briefly talk about this. For these ones, you have to think about how the work is the change. Maybe right here, I'll set a note for number 8. The work is the change in energy. So if you can calculate the initial energy of the system and the final energy of the system, those are two separate calculations. It's going to be basically the final kinetic energy minus the initial kinetic energy. And so your calculation will basically be take his initial speed is over here. Does that make sense? So like for Albert, you'd calculate how much energy did he have before he started to speed up, and then how much energy did he have after he sped up, and the difference between those numbers would be how much work he did. And what you're going to find here is that it's actually a very intuitive answer. What do you guys think is harder? To go from, say you're running, to go from 0 meters per second to 3 meters per second, or to go from 7 meters per second to 10 meters per second? 7 to 10. The math will bear that out as well. But just intuitively, the faster you're going, the more energy it's going to take to gain an extra meter per second of speed. Probably experience that in your car. Going from 0 to 30 is, you can feel the car does not take much effort to go 0 to 30, but to go from say 60 to 90, the car really has to work. If you've ever driven an old car, you know the car has to work pretty hard.
Yeah.
If you've ever driven an old car for years and then you get a brand new car, you'll find yourself on the highway being like, wow, it went way faster than I thought because the car's not rattling. You go, oh, I'm going 100 miles per hour and the car's just going so smooth, you know? All the time. Okay, so potential energy. Here, I'll demonstrate it for you. Okay, when you take, I showed this to you yesterday, I'll show it again. So there's two different paradigms here you can kind of use. One is, if I lift this object up and then I let go of it, I can say, well, what's happening in terms of energy? Well, I can say, oh, the gravitational field is exerting a force over a distance to push it down. And so, the gravitational field is doing work on the object to give it energy. That's one perspective. The other perspective is, when I lifted it, I stored potential energy in the Earth doodad system. And that energy is, this is the paradigm we're going to use most of the time, is when I lift it, I've stored energy in this system. And so when I release it, that stored potential energy is converted into kinetic energy. Does that make sense?
Yes.
Are there any questions on that idea, the general idea? It's like we talked about yesterday. When you like say squish a spring. Oh, look, I squished the spring. I stored energy in that spring. And when you release it, that energy is released, transferred to something else. There's a billion zillion examples of storing potential energy in something. That's what, with the projectile, the gun, that's exactly what's happening there. That gunpowder has chemical potential energy that's stored molecularly inside that material. And then when it's ignited, that chemical energy is converted into heat and noise and expansion. So, the wrong thing. Anyway, so 11 just looks like this. It's easy peasy. A block of mass M is slowly lifted from ground level at constant speed. So here's ground. Here's the block. Okay? Block of mass M. It is slowly lifted up to a final height of h meters. Okay? How much force did the winch need to exert on the block in order to lift it? Well, there's gravity is mg, right? So the amount of force required is mg, right? In practice, what would happen is you'd exert a little bit more than this to get it accelerated, and then once it's at the speed you want it to be at, you would just level it out and exert, and they'd be equal and opposite forces. Okay? So you lift that up. So that's the answer to part A is mg. How much work was done? Well, okay, I know that work is force times distance. So the work would be how much force? mg. How much distance did he cover?
H.
This is famous, okay? Although we're going to write it a little bit. The work done to lift an object a distance h is mgh. And then what's the block's final potential energy? Well, all we do is we make an argument that, well, the way we would choose to think about this is that since we know that that energy is going to be converted back to kinetic energy eventually, we're going to think about it in terms of, that's the letter, it's U. There you go. So that's C, the potential energy. Potential energy. And then part D, what happens to the block's potential energy if you release that? Well, it's going to, well, what's going to happen is this potential energy is going to get converted to kinetic energy. So the answer to D is potential gets converted to, now of course, that's a very fancy wordy way of saying a very simple thing, right? Which is when you lift something and let go, it falls, right? It speeds up, right? So, but the thing we're doing here is we're constructing a sort of a mental framework of how to think about things and how the relationship between, say, the height of an object and how fast it's moving when you drop it, okay? E says, just before the block hits the ground, it's traveling with velocity v. Write an equation showing the conservation of the block's total mechanical energy. So here's what it would look like. How much energy is up here? Well, up here, you'd say the total energy, so total energy is potential energy, mgh, plus how much kinetic energy does he have up here? If he's at rest? Zero. So this is potential, this is kinetic. So his total energy is potential plus kinetic. That's all the energy he has. Then at the bottom, down here, how much potential energy does he have here if his height is zero? Zero. And now all of his energy is kinetic. And so what's going to happen for the last part of this question is, now the equation, of course, would be energy is conserved. So the total energy is conserved, and so this has to equal this. So you might be wondering, why write the zeros? Well, the zeros help us see that, so this is the answer to part E, is his total energy at the top, potential plus kinetic, is equal to his total energy at the bottom, potential plus kinetic. Now, it just so happens that the kinetic at the top is 0 and the potential at the bottom is 0, but you can probably imagine would it be difficult to come up with a problem where we wanted to know, say, how fast is he traveling when he's this far off the ground? Well, okay, then you would just throw an extra MGH term. Anyway, what's the answer to the last question is, it says, can you solve for V? So what do you get if you solve this for V? Well, what cancels out, first of all? The M's cancel. 2 comes up here. And then you take the square root. Hopefully recognize this. This is a result we've seen before. This is a result that showed up in kinematics. This is actually the result of a pretty difficult question in kinematics, where you reason out that, you guys remember this? Hopefully, we talked about dropping a bowling ball off the top of a building and saying how fast it would be moving when it hits the ground. And anyway, so now in this different framework, even though we're talking about energy, you end up, well, you ought to, right? If you didn't, then you're in trouble. Same result. So there you go. Tomorrow we'll try to do a combination of some work time and go over a couple more things.